Hello, and welcome to this virtual lecture course on the quantum theory of condensed matter. I'm Dr. Andrew Mitchell, and in this lecture I want to talk about solving tight binding models. In the previous lectures, we introduced the second quantization formalism for quantum mechanical many-body problems, and then we looked at a particular class of models called tight binding models. These are quadratic Hamiltonians, meaning that we have these creation and destruction operators appearing in pairs in the Hamiltonian, and they describe non-interacting many-body fermionic systems. In particular, they are a good way of describing a wide class of materials in condensed matter physics, which have, for example, an on-site potential describing a potential energy background from a lattice, but also allowing the electrons to quantum mechanically tunnel from one atomic orbital to another. These can describe a range of metals, insulators, and also more exotic systems, as we'll see. In this lecture, I want to talk about really solving these models. We saw last time how we can, in general, solve such quantum mechanical models by formulating the Hamiltonian matrix in the many-particle basis and just doing a brute force diagonalization. But we also saw that because these systems are quadratic, that there's an alternative. In particular, we can look at writing down a diagonal form of the Hamiltonian operator itself. And this is something that we can do by performing a canonical transformation of the original operators of our system. So I want to look at that today explicitly. I'll actually do some numerical calculations within the computer package Mathematica, which allows us to set up some simple systems. I'll look at a class of 1D systems in this lecture, and just diagonalize these systems, look at the eigenvalues, look at the wave functions, look at the spectral properties, and so on and so forth. So we'll do that in the lecture today. And then we'll also, moving away from this brute force numerical diagonalization, look at how for periodic systems describing lattice fermion problems, metals and insulators and so on, in real material systems, because of the periodicity, we can actually use a Fourier transform as a specific type of canonical transformation to diagonalize the Hamiltonian. And in so doing, we'll have a description of the eigenstates and eigenenergies in the Brouwer zone, which describes the reciprocal space of momentum space. This will allow us to look at these problems in a different way. In particular, it'll allow us to identify the band structure of these systems. If we have a single site per unit cell, we have a single band. If we have a two-site unit cell, already we have two bands, and then there's the possibility that that could be an insulator or a metal, as we'll see. We also have more interesting things coming up, for example, the possibility of having topological quantum matter, and we'll discuss that probably in the next lecture. But this lecture will certainly set the scene for writing down these kind of models and looking at some of the structures for these systems. Okay, let's get down to work.
So in this lecture, we'll be discussing the solution of tight binding models. In the previous lectures, we saw how we could formulate tight binding models within the second quantized language. We saw how these tight binding models can represent electrons moving in some potential background due to a lattice, and also the electrons can tunnel from atomic orbital to atomic orbital, giving them some kinetic energy. These kind of models are so-called quadratic Hamiltonians, meaning they correspond to non-interacting fermions, as we'll see more today. So the general technique for solving tight binding models we looked at in the last lecture. One can do a brute force calculation where one really formulates the Hamiltonian matrix itself in the many-particle basis and diagonalizes that. But because these systems are quadratic, there's a simpler way, an exponentially simpler way, as it turns out, which is to diagonalize the Hamiltonian operator itself, and that's the general strategy one uses for such models. So if we have n orbitals in the system, then the Hamiltonian matrix is 2 to the n by 2 to the n, whereas the Hamiltonian operator could be written in matrix form just in terms of an n by n matrix, which is obviously much simpler. By performing a canonical transformation of the creation and destruction fermionic operators, one can find a diagonal representation in which one has single particle states and energies. This is essentially equivalent to the band structure, and we'll talk about that a bit more today. And to generate the many particle states and many particle energies, it's actually rather simple. We think of a Fermi energy and just filling up these single particle states until the Fermi energy, and then we can construct the many particle states just in terms of the direct product of the vector spaces for these single particle states. So we explored that in the previous lecture. So in this lecture, we'll be going a bit further and actually doing some actual calculations involving also some numerical calculations, and I'll show you how those work, as well as some analytic calculations where we can perform the diagonalization for certain systems analytically using a Fourier transform. So we'll do examples of both. So first of all, let's remind ourselves what the type-binding Hamiltonian is. Type-binding Hamiltonians are quadratic Hamiltonians. So we have a Hamiltonian operator that is of this general form. We have creation operators Ci dagger, and we have destruction operators Cj, and we're summing over all of the sites in the system I and j. So this is a quadratic Hamiltonian because we see pairs of creation and destruction operators only. We don't see any terms in the Hamiltonian which involve 3 or 4 or a larger number of operators. And it's really this property of just having pairs of operators that allows us to do a canonical transformation to bring this to diagonal form. One other thing, it's quite traditional to let the diagonal components of this tii, be the on-site energies. So this is like a potential, if you like, for a particular orbital I. And also, by hermiticity, we require that Tij is equal to Tji star, the star meaning complex conjugation. And by actually combining those two equations, you also see the energies there, epsilon I, also have to be real. Okay, so that's the Hamiltonian we're working with. Let's just remind ourselves of the general strategy. We form a vector operator. This is a vector of operators. At some point I will stop writing hats on top of the operators just for brevity of notation, but for now I'll keep them in. So we form a vector like this. The corresponding destruction operator vector is just the dagger or the adjoint of this vector I've written down, which means that the individual operators get daggers, but also the column vector turns into a row vector. Or you could think about these as matrices. This is like a row matrix, and C vector is a column matrix. And so, having introduced vectors for the operators, we can write the Hamiltonian in a compact form. We can write it without the sum now, because we let the matrix algebra do the double sum for us. We simply say that the Hamiltonian is C vector dagger T C vector, where this T here is a matrix of numbers, or coefficients if you like, parameters in the Hamiltonian, not operators. So you see there's no hat on the T there. And in particular, this T is extremely simple to read off from our original Hamiltonian. It's just T11, T12, T13, and so on, T21, T31, and so on. It's just a matrix of those parameters. And so we're able to write our Hamiltonian in a nice compact fashion. And just to convince you that this all works out, we could imagine really just writing this whole thing. So imagine that we have this big matrix product here of all of these things. And so on. And then I have this vector of destruction operators on the right-hand side. And you write all of that out. Imagine doing the matrix multiplication of these things. And I will end up, indeed, with this, which is what we want. So this is just a nice compact way of writing Hamiltonian. But now that we have it, we can perform a canonical transformation of the operators. And the operators that I'm talking about are the C and C dagger operators. Specifically, I'll let C is equal to U times F, where F is some vector of operators. And I'll just write that over here. So F would, a vector operator, be F1, F2, F3, and so on. And the U here is a unitary matrix. Which basically just tells you how you scramble up all of the F's to get the C's. Okay, very good. And of course, because these is a matrix product, this is just a linear equation. And the whole point is that when I substitute this into the Hamiltonian, I get the following. And what I want is for this to be a diagonal Hamiltonian. Where this, this D matrix, this D is a matrix, is just defined as being U dagger T U, such that it's a diagonal matrix with elements k, k primed equal to the delta function Kronecker delta k, k primed, meaning that there's only non-zero for k equals to k primed, and the element along the diagonal is called epsilon k. So if we were to plug in this definition of the D matrix into our expression for the Hamiltonian written in terms of the F's, we simply get that H is equal to the sum over K of epsilon K F K dagger F K. So I'm going back to the non-vectored notation now. And we had previously a double sum, and now we have a single sum, and that's achieved precisely through this diagonalness of that matrix with that Kronecker delta in there. So this thing that I've written down here, this Hamiltonian, is a Hamiltonian in diagonal form. And it's the kind of Hamiltonian we actually studied in the previous lectures. It's a free electron gas. We imagine a bunch of totally uncoupled quantum orbitals labelled by K, with corresponding operators Fk and Fk dagger. And each of those uncoupled orbitals has some single particle energy epsilon k. To construct the many particle states, we just fill up these single particle states. Good. How, then, do we actually find this particular canonical transformation that achieves this? Well, that's the usual process of diagonalizing some matrix, we take a matrix T and we diagonalize it. How does that work? Well, we have to do what's called a similarity transformation. That's this object. We have to find a unitary matrix U such that U dagger TU is diagonal. When we do that, we get the energies along the diagonal elements of D. So they're the eigenenergies. They're something that, of course, we need. But we also get the wave functions. The wave functions, these are single particle wave functions, but still, because from this equation telling us about how the C's relate to the F's, and noting that the matrix U is unitary, we can write, of course, U dagger U is equal to the identity matrix. That's the definition of it being unitary. Therefore, U dagger is the inverse of U, and therefore I can invert this equation and write that the F's are equal to U dagger times the C's. So that means that I can write a given F, Fk, as the sum over I of U I k times the Ci's. So these parameters of this unitary matrix, or the elements of this unitary matrix, which I've labelled UIK here, tell you about the amplitude of a given real space orbital I in the eigenbasis of K. So for a given orbital in the diagonal basis, K, with operator Fk, I can write that as a linear superposition of the single particle states in the original real space basis labelled by I, and the amount of each of those orbitals in the real space basis that arise in the diagonal basis is precisely this UIK. So these UIKs, so this matrix U is basically a matrix of vectors, and those vectors are the eigenvectors. Those vectors really are the wave functions, if you like. If I were to take the square modulus of these UIKs, it would be the probability amplitude of finding a particular real space orbital labelled I in the diagonal basis of K. So this is the general setup, and before moving on to talking about band structures and talking about some analytic ways of actually doing this diagonalization using the Fourier transform, I just want to emphasize that if I have some arbitrary Hamiltonian, which is quadratic, a tight binding model, I can always just formulate this matrix T, and then I can diagonalize it, and then that's basically the solution of the model. In particular, I can do this numerically. There are many computational or mathematical packages which allow you to just diagonalize matrices, and in practice, on the computer, you can diagonalize fairly large matrices, so things that you wouldn't, of course, be able to do by hand. I mean, even doing a 3x3 or 4x4 matrix by hand is a pain. But on the computer, you could quite easily, using standard packages, diagonalize matrices of dimension 1,000 by 1,000. If you have a powerful computer and you want the exact eigenstates, you can maybe even go up to 100,000 by 100,000, something like this. Which means a system with 100,000 orbitals, which is large. Okay. What we'll do now is actually just take a couple of examples and study those using a numerical package called Mathematica, which allows us just to write down the Hamiltonian matrix, diagonalize it, and plot the eigenvalues, plot the wave functions, and just investigate some of the physics of these systems. So I want to talk in this section about two sort of toy models. One is going to be a 1D tight binding model. And in pictures, it's going to be something like this. We imagine that there's a bunch of orbitals coupled in 1D, and these will have energies epsilon, and I'm going to keep the same epsilon on every site. And I'm going to imagine that there's a quantum tunneling between the orbitals, denoted by these horizontal bonds here, which is going to be T. And there's going to be n sites in the system in total. And because I want to do a numerical diagonalization of this system, I'm going to have to keep n finite. One thing I could do was join up the first site here to the end site and form a ring, and that would have periodic boundary conditions. Alternatively, I can just leave it as a chain like this, and you'd refer to those as open boundary conditions. The Hamiltonian for this 1D chain is simple enough. It contains a term where I sum from 1 to n of epsilon ci dagger ci. They're the on-site energies. Ci dagger ci is the number operator, so it just counts the number of electrons in a given site, and if it's empty I get 0, and if it's occupied I get epsilon. So that's like a potential energy term. And then I have the term which tunnels electrons between neighbouring sites. And here I sum from I equals 1 to n minus 1, and that's because I tunnel an electron from site Ci to site Ci plus 1. If I can tunnel an electron from I to I plus 1, I must also allow the electron from I plus 1 to tunnel back to Ci. That is like a time reversal symmetry, and it's also demanded by the hermiticity of the Hamiltonian, so I write the Hermitian conjugate piece explicitly here. And the way I've written it, this T is a real number, and the epsilons are real numbers. So that's the 1D model, describing electrons moving down this 1D chain. And you can imagine in a continuum, maybe if you had many sites with a very small distance between them, with the open boundary conditions here, this is almost like particle in a box. We imagine that the electrons can sort of move up and down in this one dimension, but they can't go beyond the first and last sites. Okay, so we'll actually see that the eigenstates of this system resemble these particle in a box states. Good, so that's the 1D tight binding model. It's a one-band model, so-called, and that's because we have a unit cell that just contains one orbital. What do I mean by that? Well, we imagine a unit cell that sort of looks like this, with a particular site and a bond coming out from that site. And then we can translate that unit cell by one lattice constant, which is a distance, let's call that A0, and we copy that unit cell, place it down when I've moved it one A0 to the right-hand side, and then keep dumping this unit cell one lattice side to the right, and in so doing I generate the entire 1D chain. If I had a 2D square lattice, I would have a single site that was copied as I move to the right, but also copied as I move up and down, and then that would tile the two-dimensional plane. We'll come on to discussing that a bit later. Good, so this is a 1D tight binding model. The other model that I want to discuss is the so-called SSH model. This is the Su-Schrieffer-Hager model. And this is very similar. It's a 1D tight binding model. So again, I have these orbitals in 1D. Again, they have energies, on-site energies epsilon, which are all the same. But this time, I have alternating tunneling elements. So T1, T2, T1, T2, T1, T2, and so on. And so in this particular system, we have a unit cell which contains two orbitals. So this will be a two-band system. So we have a unit cell now that looks like this. I have one orbital connected to another. This internal bond here can be T1, and this one that's leaving can be T2. And I just copy this, this unit cell, this time by 2A0, because I have two real space sites in the unit cell, and this translating this thing by 2A0, dumping it down, moving again by another 2A0, dumping it down, and so on. This generates the entire 1D SSH model with these alternating bonds. And so actually we can write that 2A0 here is basically a new lattice constant we'll call A0 primed. It's the lattice constant for the unit cell rather than for the individual atoms. Okay, so let's write down the Hamiltonian for this SSH model. We have a term here which just involves the energies. I'll write the operators within the unit cell as Ci, where I is going to label the unit cell, and then the two orbitals in the unit cell are going to be A and B. So we have, for the energies, just diagonal pieces, CIA dagger, CIA, and CIB dagger, CIB. So I labels the unit cell number, and A and B label the two atoms within the unit cell. And then I have tunneling terms. I have the sum over unit cells with the tunneling within the unit cell, CIA dagger, CIB, plus the Hermitian conjugate term. And that's the tunneling of electrons within the unit cell. And then I have a term that tunnels between unit cells. And because I have n unit cells, now I need to sum from I equals 1 to n minus 1. And the tunneling amplitude between unit cells is T2. And this takes us, for example, from CIB dagger to CI plus 1A plus the Hermitian conjugate, CI plus 1A dagger, CIB. So it looks a bit more complicated, but you can see in pictures it's very similar, and it's actually rather simple. I have a single on-site energy epsilon. I have just a 1D chain of orbitals. I label a given unit cell I. This is I equals 1, this is I equals 2, I equals 3, I equals 4, and so on. And then within the unit cell, I have orbitals A and B. So let me just make a note of that. So the I labels unit cells, and then A and B label sites within unit cell. Okay, so these are the two models that I want to look at, and next what I want to do is show you the actual numerical solution of these two models. I will write down the Hamiltonian in a matrix form. This is basically equivalent to finding this T matrix. And then I will just diagonalize numerically this T. I will extract the energies, the eigenenergies, these are the single particle energies, and I'll also extract the wave functions which are contained in the matrix U, which does the diagonalization for us. And that will allow us to plot, for example, the wave function amplitude of a given state in the original orbitals in real space. We'll also see that there are some interesting phenomena of these two models. The first model is basically a metal, and the second model is basically a band insulator. And we'll also see something funny happening in the SSH model, depending on whether the chain terminates at the end with either a strong or a weak bond. That has something to do with topology. We won't discuss that in this lecture. We will just do the brute force calculation and see what we get. Okay, so let's take a look at that now. Okay, so what I want to discuss here is an actual numerical calculation for the 1D type binding chain. I'm using a program called Mathematica to do this, which is a beautifully simple and powerful program. It allows you to do all sorts of wonderful things. So here what I've done is to set up a system in which I have basically a 1D type binding model of n sites, and if I have just two sites coupled to each other, I have on-site energies epsilon here on the diagonal, and then tunneling matrix elements between them of T. And this bit of code that I've written here just generates any size of Hamiltonian matrix that I want. And this, so this shows this sort of tridiagonal structure with the on-site energies epsilon on the diagonal and off-diagonal elements being T. So this is tunneling of electrons down a 1D chain. So let's pick specific parameters. I can choose an epsilon of 0 and a tunneling matrix element between neighbouring sites of 0.5. And what I can do is just diagonalize this Hamiltonian to find the single particle levels. Let's have a look at a 9-site system. And here I see there are 9 eigenvalues for the 9 sites in the system. And these are, of course, eigenvalues for eigenstates that are delocalized over the whole system. And you see that there's a range of energies, and in particular there's also an energy sitting exactly at 0 in this particular system. Okay, let's have a look instead at the eigenvectors. So, as we know, the eigenvectors are actually contained in a matrix U, which can be used in a similarity transformation to diagonalize the Hamiltonian. In particular, the rows of this matrix are actually the different eigenstates, and the different numbers here. Let's have a look at the first one as an example. This is the first eigenstate. These different numbers here show you the wave function amplitude of a given eigenstate in the original basis of real space sites along the chain. So each of these numbers here tells you about the wave function amplitude in the original basis. And what I can do, in fact, is do the entire similarity transformation, U dagger. Here the dagger is actually equal to the transpose because I'm just working with real numbers in this system. And this performs a similarity transformation, and if I've got the right transformation matrix U, which is the matrix of eigenvectors, this should diagonalize the Hamiltonian, and indeed we see that's the case. Furthermore, if you look at what the elements of the diagonal elements of this matrix, you see that they match up perfectly with the eigenenergies from just diagonalizing the system. So indeed, this is the correct transformation. We have a diagonal matrix, and the diagonal elements are the energies of the system. And the elements of the matrix U are the eigenstates. They're the wave functions, if you like. Okay, let's expand this to a much bigger system. Let's look at a chain of length 100, and I can just diagonalize this system and plot the energies on the vertical axis here as a function of, and it's just really an index which tells you what the different eigenenergies are. And you see that you actually get this kind of cosine dispersion. It's telling you that the energies of the system take a particular form, and the most important thing to note about this is that the energies are bounded. So even though I have 100 sites in the system, the energies only fall into this window between -1 and +1. If I were to look at an energy less than -1, I would see there was no states with that energy. If I were to look at energies above +1, I would see again there was no energies, no states with those energies. But between -1 and +1, I see that there's actually a sort of band of energies, and at any given energy I might find a particular state. In particular, if I were to go to the infinite size system in the continuum, this line would, instead of being discrete points, 100 different points for 100 different sites, I would see a whole continuum line, and at any given energy I would find a particular density of states. This would form then a band of a continuum set of states, and outside of the band I have zero density of states. I can also look at the wave functions. Again, I can just plot the wave function's amplitude as a function of site index, and so what's plotted on the y-axis here is the square modulus of the wave function amplitude, or the wave function, which is the wave function amplitude, and on the x-axis the site index along the 1D chain. And what you see is essentially something that looks a bit like a particle in a box. You see that the wave function has this sort of smooth, continuous form. It's strongly peaked in the middle of the box, which tells you that there's a large probability amplitude for the particle to be found, and for the particles to be found in the middle of the box. And there's sort of boundary conditions such that the wave function vanishes at the walls. Again, if I were to go to an infinite size system, I would see this wave function was totally delocalized over the whole system, subject to these boundary conditions of the vanishing wave function at the edges. I can look at other wave functions. That was just the ground state, but let's look at the first excited state. And then I see in here that I get a node in the middle. Again, this is very reminiscent of particle in a box with these kind of structures. So you see that by diagonalizing these systems, you can really reproduce all of these classical results, and of course go a lot further to look at any more complicated system. One such very interesting system is the so-called SSH model, which we'll discuss in general, and much more detailed in what follows. This is basically a 1D chain. We have on-site energies epsilon as before, but this time we have alternating hoppings between neighbouring sites. The first two sites are coupled by T1, the next two sites are coupled by T2, T1, T2, T1, T2, and so on. So I still have a tridiagonal matrix. It's still a one-dimensional system, but now I have these alternating tunneling matrix elements. So what does that do to the structure of this problem? Well, let's have a look at the energies of the system by diagonalizing this Hamiltonian. And what I've plotted here are two different scenarios. We imagine a chain that starts with T1 on the left-hand side and starts with T2 on the right-hand side. So we imagine a chain, a 1D chain that goes T1, T2, T1, T2, and so on the left-hand side. But on the right-hand side, it goes T2, T1, T2, T1, T2, T1. So the only difference between these two are the kind of boundary conditions, what it looks like at the end of the chain. If you're deep in the middle of the chain, it just looks the same, alternating hoppings. Also, I've plotted here explicitly T2 is equal to 0. And what I see with T2 equal to 0 is actually something that looks very similar, but there's an important difference between these two scenarios. At T2 equals 0, what that does is it dimerizes the whole system. I have 50 unit cells in my system with a unit cell of 2 sites. With T2 is equal to 0, I just have 25 sort of dimerized pairs which are decoupled from each other. And each dimer has an energy, one of the eigenstates has an energy of -1, the other one has an eigenstate energy of +1, and so I just have 25 values at -1 and 25 values at +1. The situation on the right-hand side is almost exactly the same, except for the situation at the end of the chain. At the end of the chain, because I start with a T2 bond and T2 is equal to 0, then I just have an isolated sort of dangling orbital that's not coupled to anything at the end of the chain, and therefore that just has 0 energy because the epsilons are all 0. So I have 24 pairs of dimers with 2 sites left over, one at each end of the chain, and therefore you see that in the middle of the spectrum here I have just these 2 sites sitting exactly at 0 energy, and they sit in an eigenenergy gap. So on the left-hand side and on the right-hand side you see that there's a big gap where there's basically no density of any states between -1 and +1. The interesting thing is, as I switch on the T2 and couple all the sites in the system, some of the features remain intact. So I still see that there's a gap in both systems. Here the gap has now been reduced to -0.5 to +0.5 in both cases. But one of the interesting things is that on the right-hand side I still see 2 states sitting exactly at 0 energy. And this is rather interesting because they're actually now coupled into the rest of the system with a finite T2, but yet still they appear to have 0 energy. On the left-hand side, even though all the sites are coupled in together to each other, we see that there are no such states sitting at 0 energy, and there's still a pristine gap in the spectrum. As I increase the T2 further, I can close the gap, and now I have a homogeneous system when T1 is equal to T2. This is the metallic system we looked at before. We don't have a unit cell of 2 sites. Now everything just looks exactly the same as I go down the chain, and I have a cosine type behavior of the eigenenergies in both cases. This is the symmetric point where the 2 situations are equal. But as I increase the T2 further, you see now this situation swaps over. Now I have a gap reappearing, but that the states sitting at 0 energy are now on the left-hand side. So there's actually 2 different phases. Let's have a look in more detail about the low energy eigenstates of this system. Let's have a look at the eigenenergy of the lowest energy state. Delta T here is T1 minus T2, and if I look at a large delta T, I'm in the fully gapped phase, and I'll see that the lowest energy eigenstate is one that sits at the sort of lower band edge, and that's then reducing as I reduce the delta T, and as I reduce the delta T to 0, I have a metallic system, and the lowest energy state there in this discrete system of 100 sites is basically an energy of 1 over 100, which is 0.02. This is the lowest energy state in the metal. But however, as I reduce the delta T further, I go into the other phase. This is delta T negative now, and you see that we really, instead of the gap reopening and getting the lowest energy states at the gap edge, I now go into the phase where there are these pristine 0 energy states, and for this is basically a different phase, and you see the eigenenergies there are exponentially small. We get more insights by looking at the actual wave functions of these systems. Again, we look at the amplitude of the ground state. Let's have a look at the amplitude of the lowest energy states, actually, the ones around the Fermi energy, expanded in the basis of physical real space sites down the chain. So here I'm plotting the lowest 2 states, and we see that in the gapped phase we have delocalized eigenstates here. There's 2 different delocalized eigenstates. The electrons are propagating down the chain, they're delocalized, and they look like regular kind of particle in a box type states. And these are the lowest energy states that are living sort of at the gap edge. However, if I make delta T negative, I go into this other phase where the lowest energy states are these ones that are very close to 0 energy. If you look at the 0 plotted, the energy there plotted on the bottom, you see it's becoming very small. And then we see something rather different. In particular, look at the y-axis scale here. As I make delta T smaller and smaller and smaller, these states become exponentially localized at the edge of the system. So these 0 energy states in one of the phases are not delocalized throughout the system, these ones sitting right in the middle of the spectrum there, they're actually exponentially well localized at the edge of the system. And of course, in the dimerized limit, when T2 is equal to 0, we expect, indeed, that there are these pristine zero-energy states perfectly localized. The interesting thing is here, even when T2 is finite and those states are coupled into the rest of the system, they are exponentially low in energy, and they're exponentially well localized. So all of this has something interesting to do with topology, and we'll be talking about that in a lot more detail in some of the future lectures. So hopefully that gives you a sense of how one can solve arbitrary type binding models. We simply have to write down the Hamiltonian operator in a matrix formulation and then diagonalize that matrix. The interpretation then is in terms of these single particle states and energies, from which we can understand the many particle states and energies in a rather straightforward fashion. One could imagine, for example, writing down a 1D model with disorder, or a 2D model, or anything like this, and this method that I outlined always works. However, one is of course always limited to finite system sizes. So what I want to talk about now is diagonalizing periodic systems by a Fourier transform. And we'll see that it's important that these systems have a translational symmetry, a periodic periodicity to the lattice. Okay, so this is the next task. Let's consider the first most simple case. It's the 1D wire again. So we have a 1D quantum wire. I'm going to write down the Hamiltonian. We've seen it before. I'll label positions in real space x in this calculation. And what I'm going to do is consider an infinite wire now. And I'm imagining that the tunneling matrix element between sites x and its neighbours, x plus or minus 1, is just given by this t. And because t is independent of x, I have a periodic system. It's translationally invariant up to the lattice constant. If I were to have in this equation tx here, the t depended on the spatial position x, then there would be, in principle, an infinite amount of information contained because I'm summing over infinitely many sites. And there would be no analytic solution to such a problem because obviously I would have an infinite amount of information. Here, there's not an infinite amount of information because I have a constant, t for all sites. So this would, if you were to write down this in a matrix form, it would be a tridiagonal matrix with the t's on the leading off-diagonal elements, but the matrix would be an infinite dimensional matrix. So we would not, of course, be able to solve this kind of thing numerically, but because of the simplicity of this model, it turns out that we can solve it analytically by using a canonical transformation of the operators to bring the system into diagonal form. So the idea is that we have a 1D type binding model, just to sketch it out in cartoon again, and this goes on forever in both directions, and I'm imagining that I have a single site unit cell, and I can translate this to the neighbouring unit cell with a lattice constant A0. That's the real space distance measured in meters, if you like, that takes one unit cell and places it on the next lattice side to generate the entire system. So what we'll do, let's leap straight into it, is do a Fourier transform of the operators. So let's suppose that these operators Cx will be written in terms of these new operators Ck. And so the coefficients, which previously I labelled Uik, are now actually known to us analytically. They're the Fourier coefficients. And just to unpack what's seen in this equation here, this n is the number of sites on the lattice, or the number of unit cells, and n goes to infinity because we have an infinite dimensional system. The real space is connected to momentum space through the Fourier transform, so k is actually the momentum. So this is actually sort of kx, if you like, the momentum along the x direction. This is the reciprocal space for of real space, it's momentum space. This I in here is square root of -1, the complex number. It's not the real space position. The real space position is x, and A0 is the unit cell. The lattice constant. So I'm basically just transforming from the Cx to the Ck's. And also, if I want to think about the Cx daggers, they are obtained from the Cx's by taking the dagger. And so obviously I have an equation for those as well, which is almost exactly the same, except minus I, kx, A0, ck, dagger. And the minus in there is coming because when I take the dagger, I have to do the complex conjugate, which turns the I into minus I. With C, these two equations tell us how I can write Cx's in terms of Ck's. I can also do the inverse transformations and write down the Ck's in terms of the Cx's. And I can do that because the Fourier transform is invertible. So let me just write that down in this little box here. So we have it all on one page. I can write down very simply that Ck is equal to 1 over root n, and this time the sum over real space operators x, and then it's e to the minus I k x A0 of the Cx's. So when I go from the Cx's to the Ck's or the Ck's to Cx's, it's basically the same equation except that I get this additional minus sign in the Fourier component. Okay, I can also write down the analog of this equation, which tells me that Ck dagger is equal to 1 upon root n, sum over x of e to the, and then this time plus I k x A0 of Cx dagger. Okay, so again, these are the corresponding equations. So they're basically everything we need to go backwards and forwards between real space and momentum space. At the moment, these are just arbitrary looking transformations. I've pulled them out of the hat from nowhere, before we continue, we should actually confirm that these transformations are actually canonical transformations. Remember from the previous lectures, the only kind of transformations we're interested in are transformations that are canonical, because canonical transformations, by definition, are the ones that preserve the fermionic anti-commutation relations. If we transform from CX's to CK's, and the CK's do not obey the fermionic anti-commutation relations, then they're not fermions, and the models we write down will just be garbage. So before continuing, and we only have to do this once, but once we've done it, we know that it works, we should just confirm that this Fourier transform is a canonical transformation of the operators. So the Fourier transform of operators is canonical. Let's prove it. What we want for a canonical operator, or a set of canonical operators, is that they obey the fermionic anti-commutation relations. And there are three such relations that I need to confirm. There's the anti-commutator of CK and CK primed. There's the anti-commutator of CK dagger, CK primed dagger. And there's the anti-commutator of CK and CK primed dagger. And this last one, of course, is non-trivial. So let's just substitute in our expressions that we had on the previous slide for the CKs in terms of the CXs, and just see what we get. So let's take this first one. We have to transform both CK and CK primed, and so I'm going to get an overall factor of 1 upon n, so it's 1 upon root n times 1 upon root n. Then I'm going to sum over real space operators x and y. So when I substitute in the expansion of CK in terms of real space operators, I can write those in terms of CX's, but I can't use x again for CK primed, so I have to use another label, which is going to be y. And then inside here, I'm going to get e to the minus I a naught, this is a constant factor, of kx plus k primed y. And then I get a commutator of the original operators, C in the original basis, Cx and Cy. So if you don't understand that, just try to work through it yourself a moment, maybe pause the video and just work through it yourself. I've just really substituted in the expression for Ck in terms of Cx and Ck primed in terms of Cy's. These are the Fourier factors, which I've combined into one object. And then because here I have the commutator, the anti-commutator of these operators, I just get the anti-commutator of these operators. So this is pretty straightforward. And of course, the important point is that this anti-commutator here in the original basis is equal to 0 because they are fermions. So overall, because every single term in this double sum is equal to 0, the whole thing is equal to 0. So that one works. Let's move on to the next one. It's actually extremely similar. This time I just get e to the plus I a naught of kx plus k primed y. And then I get the anti-commutator in the original basis of Cx dagger, Cy dagger. And for exactly the same reason, this whole thing is equal to 0, because term by term in this double sum, the anti-commutator in the original basis of Cx dagger, Cy dagger is equal to 0, because the x and y's are fermions. Something more interesting happens when I consider Ck and Ck primed dagger, Let's see what happens. I'm going to get e to the I a naught, but because one of them is a dagger and one of them is not a dagger, I'm going to get k primed y minus kx. So there's a relative minus sign between those two terms. Furthermore, the anti-commutator of the original operators is cx and cy dagger. And that is not equal to 0. That is equal to delta xy. It's equal to 1 if cx and cy are referring to the same orbital. And so, because of that Kronecker delta in there, that collapses this double sum to a single sum, and I just get 1 over n of the sum upon x of e to the I a naught of x is now a common factor, and then k primed minus k. So this is something much more subtle than the other two anti-commutation relations, because the other two were just 0 by construction. This is giving me this complicated expression here. However, this is a very well-known function. The sum over all of these Fourier coefficients in this particular way is actually equal to the Dirac delta distribution, delta of k minus k primed. That's by definition from the theory of Fourier analysis. And so, in the end, I find that ck and ck primed dagger is actually equal to delta kk primed, or I could write it in terms of this delta distribution if it's a continuous variable. And of course, this is exactly what we want. So by exploiting this this identity in the theory of Fourier analysis, we know that indeed this Fourier transform is going to yield canonical fermions, CKs, and therefore the Fourier transform is indeed a canonical transformation. That's exactly what we want, and therefore we can use it, but is it useful to us? What we need to do is just substitute this into our Hamiltonian and see what we get. Okay, so we want to substitute the transformed operators into this Hamiltonian. This Hamiltonian is just the 1D chain in the original real space basis of orbitals along the x-axis. So we just want to substitute in our expressions for our cx's and cx plus 1s. So let's do that. We're going to get still the sum over x, but now for each x, we expand it in terms of k and k primed. So the cx will be expanded in terms of ck, and cx plus 1 will be expanded in terms of k primed. So this is starting to look much more complicated than the thing we started with, but we'll see it all becomes simple in the end. So for cx, I expand it in terms of ck, and I'm going to get e to the minus I k x times a naught. Then I'm going to get a coefficient for the expansion of cx plus 1, and that's going to be e to the plus I k primed, and then instead of x, it's x plus 1, a naught. And then I get the operators themselves in the transformed basis, which are ck dagger, ck primed. So that's the first term. The second term is just the Hermitian conjugate of this, and I'm going to get, again, some coefficients. It's going to be e to the minus I k of x plus 1 this time, a naught, and e to the plus I k primes of x and a naught. And then they get the same combination of operators, ck dagger, ck primed. And so that's kind of interesting because both of these two terms actually come with the same operators in k-space, whereas you can see these things correspond to different combinations of operators in the original real space basis. But the price I pay is that I have these different coefficients sitting in here outside the front. So one thing I want to do is actually to factorize out this +1 in this term and this +1 in that term, because apart from that, these two terms are equal to each other. So what do I mean by that? Let's just write it out again. So I have the sum over x, the sum over k and k primed. Then I'm going to factorize out this term that I mentioned. In the first term, that's e to the I k primed times 1 times a naught. And then I have the rest of the factors, which I'm going to write in this way. I'm going to write them as e to the I x a naught multiplied by k primed minus k. And that's all multiplied by the operators c, k, dagger, c, k primed. And in the second term, I'm going to again factorize out this piece. That's going to give me e to, this time, the minus I, k, a naught, not k primed, and we get the minus sign. And then the rest of it is actually the same term, e to the I x a naught into k primed minus k. And again, it's the same operators. So that whole thing, let me just write it in this rather simpler way. I've actually left out the factor of 1 over n, haven't I, in here? There should be a factor of 1 over n there, and a factor of 1 over n here from going to the Fourier transform. So this should actually be t over n. Good. And then I'll have the sum over, let me write that a bit clearer, the sum over k and k primed, the sum over x. I'm just reversing the order of these sums. It doesn't really mean too much. And then it's going to be e to the I k primed a naught plus e to the minus I k a naught times this factor, e to the I x a naught, and this is a common factor to both terms. And the nice thing about this is that we have the definition of the delta function hiding in here again. So I have 1 over n, the sum upon x, and then e to the I x a naught k primed minus k. So all of this combination of things is equivalent to the delta function, and the delta function will collapse the double sum from k to k primed. And in the end, I'll simply have t times the sum upon k of something that I will call epsilon k, c k dagger, c k, where we know explicitly that this epsilon k is equal to, actually I'll get rid of the t in this expression, that's not needed. Okay. This epsilon k, I'll absorb the t into the definition of epsilon k, is going to be t e to the I k a naught plus e to the minus I k a naught, which is otherwise known as 2t cos k a naught. And just to emphasize, I used here this identity from the Fourier series, which is that 1 over n, the sum upon x of e to the ix a naught of k primed minus k is equal to the delta function kk primed. And that collapses the double sum here to just a single sum upon k. It sets k primed in here to k, which is what we see in this expression. This piece drops out, and then the operators become diagonal. This is ck and ck dagger and ck itself. So this whole thing has indeed diagonalized our Hamiltonian. It's brought it into this completely diagonal form of the uncoupled free electron gas. This epsilon k in here tells you how the energy is related to the momentum, and that is referred to as a dispersion relation. It tells you the relation between the energy and the momentum. And of course, this k can be understood as a momentum, because we take the position x, we do a Fourier transform, and we get the momentum k. Position and momentum are Fourier conjugates. Also, notice that we have Noether's theorem. Noether's theorem tells us that symmetries are related to conserved quantities. So we have a translational symmetry in this problem up to the lattice constant, which means that I can shift my unit cell along the x-axis. And it is this symmetry of translating the unit cell in real space that implies by Noether's theorem a conserved momentum. And indeed, that's what we see in this expression. In the final expression for the Hamiltonian, we see in the diagonal form, labelled by k, that the k is conserved. I actually have an infinitely many conserved quantities in this expression here. Each value of k is a quantum number. It's something that's conserved, and the Hamiltonian does not change that. And that's because there's no scattering or tunneling from one k state to another. That's the whole point of diagonalizing the Hamiltonian. So by going to k space, we've basically labeled uniquely each single particle state by its own quantum number, which is the momentum. This is a conserved quantity by Noether's theorem. So Cx and labels the positions in real space, Ck label the states in momentum space, and epsilon k connects the energy to the momentum, which is a dispersion relation. Furthermore, we can understand what the single particle states are. So let's consider the single particle states in the real space basis. So these are not eigenstates, of course. Let's define those according to this ket of x. So it's a single particle in a particular real space orbital, and I just define that as being that I create a single electron at position x in the vacuum state, which is the otherwise completely empty system with no particles in any of the orbitals, and then I come along and I create a particular particle in orbital x. So this is not an eigenstate of this Hamiltonian, because the kinetic energy tunneling term will allow the electron to move from an orbital x to an orbital x plus or minus 1, and then once it's in orbital plus x plus 1, it can move to x plus 2, and so on. So these are not eigenstates of this particular Hamiltonian, but they are single particle states in the real space basis. Let's consider the actual eigenstates of the system. Let's have a look at single particle eigenstates in the momentum basis. I will call those, analogously, ket k defined as being ck dagger acting on the vacuum. But of course we know how to go from ck's to cx's, and therefore I can just write this as 1 over root n, the sum over x of e to the I k x a naught times cx dagger acting on the vacuum, which is precisely this expression in terms of the x states. So what this tells you is that a given single particle eigenstate labelled by a momentum k can be understood just in terms of a linear combination of these, linear superposition, if you like, of these x states. And the amplitude, or the amount, the coefficient which tells you about the expansion of a state k in the real space basis x is precisely these Fourier coefficients. And if I like, I can write this maybe in a slightly more convenient fashion. I don't know if this is maybe a little more understandable. You can write this in terms of cos of kx a naught plus I sine of kx a naught. And you see that therefore there are these sort of oscillating patterns, if you like, of these real space basis orbitals x. And if I want to know the probability to find an electron with momentum k at a given real space position x, then I just have to take the square modulus of this coefficient in here. It's the square modulus of the expansion coefficient of the eigenstate k in the real space basis x. I'll call that pkx. It's a probability of an electron with momentum k being at position x, and it's the square modulus of this. Now the interesting thing, of course, is that the square modulus of e to the I theta is equal to 1 for any theta, and so this whole thing reduces to 1 over n, independent of k or x, meaning that there's an equal probability of finding the electron at any given site in their system. The electrons are totally delocalized over the whole system. So the electrons are really spread out over the whole system in the eigenstates, and therefore this is certainly a metal, because the electrons are totally delocalized. Also notice that all the different momenta are basically equivalent in terms of where you can find the electrons, what the probability density is. And yet, if we actually look at the structure of these states, there is phase information in here. And it's really this phase information. This is a complex number, cos kx a naught plus I sine kx a naught. The fact that there's some phase information here that depends on both the position and the momentum is basically capturing all of the quantum mechanical information there. And that would give rise to possibilities, for example, for quantum interference and all of the other good stuff. But in terms of the actual probability density, the electrons are totally delocalized and equivalent. And this is basically related to Bloch's theorem. So now I want to move on to the more complicated situation where I have a translationally invariant lattice comprising unit cells, but the unit cell itself comprises more than one orbital, so multi-orbital unit cells. So most crystal lattices have a regular repeating unit cell. The lattice is therefore defined by taking the unit cell and translating it by the so-called lattice vectors. So we already looked at the simplest example of a 1D chain. So the 1D chain with a single site unit cell, or single orbital unit cell, let's say. In pictures, looks like this. And so on. And previously we discussed how this basically can be thought of as a unit cell that looks like this. And then we take this object and shift it here by one lattice vector along the x-hat direction, and that would lead to this sort of thing that I'm drawing in dotted lines here, which has that structure. And then if I copy it again, I get another one. When I copy and shift it. And thereby, by continually copying and shifting, I generate the whole system. So that's the simplest example. We already looked at that one. Let's have a look at the two-site unit cell. And draw these in different colors. Let's imagine that one of them is different from the other in some way. I'm coloring one in blue, the other one is open. And now this is my unit cell. So this time I need to copy and shift by 2a0, which I'm going to call this new lattice constant a0 primed. And again, what that looks like when I've copied and shifted it is these dotted structures. Okay, this middle one is also dotted inside, something like this. Okay, so we have this kind of structure, and again I can generate the entire lattice by shifting it around. These were the two 1D versions the two that I wanted to discuss. Of course, you could imagine more complicated variants even in 1D. Let's have a look at a 2D version. In particular, the simplest one is the 2D square lattice. So the lattice itself looks in pictures or a cartoon like this. Imagine that I have a bunch of orbitals. And then I have a bunch of bonds that connect these orbitals. In an obvious fashion. And the key point is that if I take a particular orbital, let's say this one, in the middle of the lattice, I can imagine this is my unit cell. And to generate the lattice, I need to copy and shift it along the x direction, but also I need to copy and shift it along the y direction. And so there are actually two lattice vectors which correspond to moving this unit cell to tile the entire plane. So we didn't really talk about the lattice vectors in the 1D case. We said we just copy and shift it along the x-axis. But now we have something a bit more complicated. We need to introduce the idea of a lattice vector. So the lattice vectors here, there are actually two of them. We'll call them A1 vector, which is a lattice constant A0 times a vector 1, 0, 0, and A2, which is a lattice constant A0 times 0, 1, 0. Of course, I could imagine not a square lattice, but a kind of rectangular lattice in which the distance along the x-axis between neighbouring cells was different from the distance along the y-axis from neighbouring cells. Then I would just put in a kind of primed here, for example, or I would say A0x or A0y. I've given these three-dimensional vectors. If I want to generate a 3D lattice, I would just have A3, which would be 0, 0, 1. And I would generate the lattice that way. So these vectors tell you about how I need to shift. So this one is A1, and this one is A2. And they tell you how you need to shift the unit cell to generate the lattice. And I can do any number of steps, any number of A1s to generate a new unit cell. I can do any number of A2s. I can do any number of A1s with any number of A2s, and I'll find myself a different point on the lattice. So if I imagine some position R, which is some amount P of A1 plus some amount Q of A2 with P and Q integers, then R is a lattice site. So I can just tile the entire lattice just by changing the P and Q. Let's consider a slightly more interesting 2D lattice, one that's very famous because of the popularity of graphene, is the so-called honeycomb lattice. This is a hexagonal lattice. It's a 2D lattice, it's hexagonal, and it is the lattice structure of graphene, which is this two-dimensional carboniferous chicken wire. So what does the lattice look like? Here I've drawn just a little patch of it involving these repeating hexagons. I'm not drawing the orbitals themselves. The orbitals are to be understood as being at the vertices of this structure. So for example, I imagine there's an orbital here, and there's a different orbital here. And a good question might be, how do I generate this hexagonal honeycomb lattice? What's the unit cell? Well, it might not be completely obvious initially, but staring at it a little while, you probably realize that the unit cell has to contain two orbitals, and those two orbitals are actually the ones that I've drawn here. It's this pair of orbitals. And how can I generate this two-dimensional lattice using this two orbital unit cell? The answer is that I would like to translate this green thing here that I've drawn to this position, and also to this position. Therefore, I would have red sites here, and blue sites here. And if I repeat this, I will be able to generate all sites on the lattice. So for example, if I was wondering, so let's call these A1 and A2. The vector that connects me from here to here, I'll call that A1, and the vector that connects me from here to here, I'll call that A2. Okay? And if I wanted to generate a different, any other site on the lattice, I can just use combinations of A1 and A2. For example, if I wanted to generate these sites down here, then I would take one step of A2, and then I would take minus one step of A1. And that would generate this for me. So I can do the usual rules of vector addition. All I have to do is combine vectors A1 and A2 in any integer multiples and any superpositions of those, and I'll generate the lattice. The only remaining thing is to write down what A1 and A2 are, and here you just have to use a little bit of trigonometry, but it's not so hard. It's actually equal to this, and I'm writing here a constant distance, ACC, which is supposed to be the nearest neighbour difference between the carbon atoms of this graphene lattice. And then the vector itself is √3/2 plus a half and 0. 0 because, of course, it's a planar two-dimensional system. And A2 is √3/2 minus a half, 0. So you can see from the diagram, one is going up in the y direction, one is going down in the y direction by plus and minus a half units. And as I mentioned, these things here are the carbon-to-carbon bond length in graphene. If I was thinking of another structure, for example, boron nitride or something else that happens to have a hexagonal structure, then that bond length would obviously be different. I could also think of distorted systems where maybe the length along A1 is different from the length along A2, but at least for graphene, it's a pristine hexagonal lattice as drawn like this. So this is the way in which you generate these systems with unit cells that are a bit more complicated. Here I've discussed a 1D version with a 2-site unit cell and a 2D version with a 2-site unit cell. And of course, one could imagine generalizing this to unit cells with some arbitrary complexity, and they could be arranged in, the unit cells themselves could be arranged into kind of a super lattice, which could be a square lattice or a hexagonal lattice or a triangular lattice or anything that you can imagine. So let's imagine, for example, a 2D square superlattice comprising some complex unit cell. So what I've drawn here is a 2D square lattice of unit cells. So this object here is the unit cell. And this unit cell can contain, let's say, L degrees of freedom. So although this unit cell is repeating in a simple fashion, the contents of the unit cell itself need not be so simple, and the contents of the unit cell need not themselves be a square lattice. So, for example, I could imagine something with some arbitrary degrees of freedom, such as this, just drawing some kind of cartoon here. Let's distinguish these things a little bit, make them different degrees of freedom. For good measure, let's put something in the middle. And these things are now repeating throughout the lattice. So this thing inside this unit cell does not have to be itself a square lattice. It's just some arbitrary thing with L degrees of freedom. So now I can tile the lattice with these things. And so I'd end up with something like this on the lattice. The question is, what is the Hamiltonian for such a system? Well, the first task is to work out what the Hamiltonian for each unit cell is. So let's consider a particular unit cell. We have unit cells that are repeating in two-dimensional space. Let's say that a given unit cell, for example this one, is defined by its x and y coordinates on the plane. So, for example, I would say that this is unit cell xy. I can write down Hamiltonian for just that unit cell, not the whole lattice, just the unit cell. And that Hamiltonian will look something like this. I'm going to call it hxy for a given unit cell xy. It will consist of some creation operators labelled by xy for that particular unit cell, and destruction operators labelled by xy for that unit cell. And then there'll be some matrix M, which tells us about what's going on inside the unit cell. So we have L, if we have L degrees of freedom, this will be an L by L matrix, describing what's going on inside the unit cell. Notice that this matrix M does not have x and y labels. Why is that? That is because the unit cell is a repeating unit, and it's the same Hamiltonian describing this unit cell as any other unit cell on the lattice. It's always the same because that's the whole point. We copy the unit cell and shift it. So it doesn't have any xy dependence itself. So let's just write down what these various things in the Hamiltonian look like. We have a Hamiltonian for the unit cell that's hxy. Let's write down our operators cxy. That is a vector which tells you about an orbital, let's say number 1, in unit cell xy, orbital number 2 in unit cell xy, orbital 3 in unit cell xy, and so on, all the way down to the lth orbital in unit cell xy. And that's because my unit cell contains L orbitals, as I said over here. So this is a column matrix of dimension L for L orbitals in the unit cell. And similarly, I have a matrix M, which is an L by L matrix, which describes how the orbitals couple to each other within the unit cell. So for example, orbital number 1 in the unit cell might have an energy epsilon 1. Orbital 2 has an energy epsilon 2. Orbital 3 has an energy epsilon 3, and so on, all the way down to orbital L. The electrons may be able to tunnel from orbital to orbital within the unit cell, and I'll call those T's, T12, T21, T13, T23, and so on and so forth. So this matrix describes the geometry and the structure and the tunneling matrix elements and the energies and everything. It describes the internal structure of the unit cell. So that's the Hamiltonian that we have for the unit cell. Now we need to assemble these unit cells into the super lattice. So how does that look? So we want to write down an overall Hamiltonian for the whole lattice H. That will consist of the sum over all the individual unit cells. So we're going to sum over all x and y on the lattice of H, x, y. This will now be an entire two-dimensional plane comprising these individual unit cells. But that's not all, because these unit cells talk to each other, they're coupled to each other, and we need a way of incorporating that into our Hamiltonian. And so I get additional terms. I get one term where I'm going to sum over a unit cell xy, and then I'm going to allow for a tunneling into the neighbouring unit cell along the x direction, c x plus 1 y. And this matrix P is an L by L matrix that tells you about the tunneling of electrons along the x direction from one unit cell to the next. And this could be, again, of arbitrary complexity. However, this Hamiltonian I've written is not Hermitian conjugate, or not Hermitian, I should say. I need to add the Hermitian conjugate term, which is this one. And to make it Hermitian conjugate, I need to take the complex transpose of the matrix P. So this term that I've written down here, for some arbitrary matrix P, tells me about the tunneling of electrons from one unit cell to the next along the x direction. But because it's a 2D square lattice, I have an analogous term along the y direction. And that needn't be the same matrix. In fact, it won't be generally. And so I'll call that Q. And you see the difference here is now I'm tunneling along the y direction. I'm considering the coupling between unit cell xy and the unit cell xy plus 1. And again, for the Hamiltonian to be Hermitian, I need to add in the Hermitian conjugate of that term. And that means I get a Q dagger, or conjugate transpose of Q matrix. Okay, so that's the general structure of a Hamiltonian, which is on a 2D square lattice, but each unit cell has some arbitrary complexity, and the unit cells are the degrees of freedom within the unit cells are coupled to the degrees of freedom in neighbouring unit cells in some arbitrary way. So this is a very general kind of Hamiltonian for a 2D superlattice structure. Of course, I could write down a hexagonal honeycomb lattice superstructure, in which case this model would look a bit different, but the basic principle is the same. Okay, so what do I do with this model? How do I solve such a model, and what will it tell us? So we want to diagonalize and solve this type-binding model using the Fourier transform. Here is the model written out again in one line. This first term describes the interactions within the unit cell. And I've color-coded this. That's that matrix M there describing the unit cell itself is in green. And next we see these two terms involving this blue matrix P, and this is inter-unit cell tunneling along the x-axis. And then likewise, I have this black matrix Q, which describes inter-unit cell tunneling along the y direction. So we have interactions within the unit cell and between unit cells, and because we're talking about a 2D square superlattice, we just have nearest neighbour tunneling events between neighbouring unit cells. And notice that the vector of operators cxy is an L-dimensional vector, and the matrices M, P, and Q are L by L matrices. So we want to diagonalize this Hamiltonian. How do we do that? We will let the vector of operators cxy be equal to 1 upon square root of n, where n is the number of unit cells in the system, and we can send that off to infinity. And let's look at the Fourier transform of these operators along the x direction. So I'm going to let this be a sum upon kx, the momentum along the x direction. And again, by Noether's theorem, I know that because there's a translational symmetry along x, there is a corresponding conserved momentum along x, and that's this object kx. And I have to label the momentum kx this time because, of course, I'm looking at a two-dimensional system, and in the end I'll have kx and ky, momentum along x and y. So I get this Fourier coefficient, and I'm going to relate that to an operator vector where I've transformed the orbitals along the x direction to momentum space, but the orbitals along the y direction are still in real space. So this is kind of a slightly weird object. It's in a mixed basis of momentum along x and real space along y. So I just want to do this in two steps, just so you see what's happening. And with that definition, and noting that the corresponding annihilation operator is just the dagger of this thing, which all it does is turn the daggered operators into not daggered operators, and importantly, of course, in this Fourier expansion, I have I goes to minus I as I take the complex conjugate. I can just substitute that into my expression and we'll see, for the Hamiltonian, and we'll see what we get. Okay, so this is what we get. It's a complicated expression with a big zoo of terms here. Let's just work through them term by term. So first of all, I'm substituting this expression for the operator vector cxy and the corresponding annihilation vector cxy into our original Hamiltonian. So I still have a sum over x and y unit cells. Because I have two factors, one of the creation, one of the annihilation operators in every term in the Hamiltonian, I get an overall factor of 1 over n out the front. And then I'm transforming the x direction into a kx momentum. I have two operators, so I need two different momenta, which I'm calling kx and kx primed. I have to double sum over both of those. Then I just substitute those expressions in. I write the operators first, and then I just pull out this coefficient, this Fourier coefficient, which is in the end, of course, just a number, so of course we know that it commutes, and here are these factors appearing here. The first term is to do with the intra-unit cell interaction, the interactions within the unit cell. That's what's written in green here. And what we see is the matrix M as before, the L by L matrix of parameters, and then the Fourier coefficients I've pulled out and factorized here, e to the ix into kx minus kx primed. And we'll recognize, of course, that this will be a delta function later on. On to the next term. In our original Hamiltonian, we have these blue terms, the inter-unit cell tunneling along the x direction. So here I have the operators c kxy and dagger and c kx primed y. And because in our original expression here, we have operators x and x plus 1, operators x plus 1 and x, we have, as with the 1D chain, this extra factor here coming out of e to the minus I kx primed. That's coming because of this extra plus 1 in here. And likewise in the Hermitian conjugate term. And that's for tunneling along the x direction. Finally, in black, we have tunneling along the y direction between different unit cells, and it's the same deal. We have a plus 1 in the y, a plus 1 in the y, but we're not transforming the operators along the y direction, so that doesn't matter. The x index is the same in both of these two terms, and therefore we don't get any extra factor. That's just these usual Fourier factors here. So now we're going to use the familiar identity from Fourier series for the delta function. And this is the identity that we had before. So we're going to substitute that in, and we'll see that this becomes much more simple. So when we use the expression for the delta function into our Hamiltonian, we obtain the following. Let's work through these various terms term by term again. The first term, again in green here, just describes the interactions within the unit cell, and we see that this has now become diagonalized in unit cell space. So the k and k primed sums have been collapsed to a single sum over kx due to the delta function. And because this term is diagonal in y, this term is now overall diagonal. What about the tunneling along the x direction? These terms have actually become also diagonal using the Fourier transform because all of these terms have common y, and y is not being transformed, but the x's have been transformed into kx's. Again, the delta function is used to collapse the double sum. We just pull out these extra residual factors of e to the minus I kx and e to the plus I kx. But you see from the operators, this is actually diagonal in unit cell space. The problem is along the y direction, because this is not diagonal. We didn't transform along the y direction. We still have real space y, and we see that these q terms in black are not diagonal. They still involve these off-diagonal terms. However, before we proceed with the Fourier transform along the y direction, let's just tidy this Hamiltonian up a little bit to make life easier for us. So what I see in this slightly rewritten form of the Hamiltonian is I've collected all of the diagonal pieces together, and we see that the matrix involved there is something a bit more complicated. It's the sum of m and p e to the minus ix plus p dagger e to the plus I kx. So that's the thing that's featuring now in this diagonal term. And as I mentioned, we've still got non-diagonal terms along the y direction, parameterized by q. So what we need to do is another Fourier transform along the y direction, and that will diagonalize the q. Let's do that now. So we'll perform a Fourier transform along the y direction in this fashion, and we'll see now in this equation that we are transforming to operators that are fully in momentum space, both kx and ky. So I did this Fourier transform in 2 steps to illustrate this point. Of course, once you've done it a few times, you'll be able to do these 2-dimensional Fourier transforms in one go. But I thought here it would be nice to see it just done out explicitly in 2 steps. So this is the transformation we're going to perform onto the Hamiltonian that we just had. And when you substitute that in, you get the following. So we've substituted it in, and this is what we get. We see a bunch of terms. We have the old diagonal terms here are now not quite diagonal because we have a coupling from ky to ky primes, but we're going to play the same game because we have a sum over y, 1 upon n, and then these Fourier factors, and again that's going to give me the delta function. Likewise, on these terms involving the tunneling along the y direction, we again have these similar kind of factors that are going to give us the delta function. And in the end, when you use that and tidy it up a bit, we'll obtain the following result. This Hamiltonian is now completely diagonal in unit cell space. I've transformed, using the Fourier transform, which is a canonical transformation, the unit cells located at xy to unit cells in momentum space labelled by kx and ky, and you can see from this expression that this is diagonal in kx and ky. And everything else has been absorbed into this single matrix E. What form does E take? Well, let's write it down. And we see that this matrix E is a matrix that's a function of the momenta kx and ky. So the whole matrix depends on kx and ky. Each element of that matrix depends on kx and ky. And it does so through this form. So we have a constant piece, which is m, the interaction within the unit cell. And then we have k-dependent pieces along the kx direction involving the matrix P, and then ky-dependent pieces involving momentum along the y direction involving the matrix Q. And so once we know M, P, and Q, then we can just write down this matrix E. And then we have a Hamiltonian that is diagonal in unit cell space in the momentum kx and ky. And so finally we arrive at this Hamiltonian, which is diagonal in kx and ky. But we are not yet finished, because this matrix E in here is not itself diagonal. This is something that depends on M, P, and Q. So we're not completely in a diagonal basis yet. We have reduced the problem from an infinite lattice of coupled sites to an L by L unit cell of coupled sites. This matrix, after all, is an L by L. So we've not completely diagonalized the system yet. We've diagonalized from an infinite by infinite system to an L by L system, so we've done very well indeed, but we've not yet completely diagonalized the system. To completely diagonalize the system, we need to do another canonical transformation that diagonalizes this matrix E. And furthermore, since E depends on kx and ky, we'll need to diagonalize this matrix for each individual set of kx and ky. So for every single value of kx and ky that I can think of, I'm going to have to diagonalize this matrix separately. And when I do that, it will tell me about all the different bands in the system, and I'll have L different bands for L different eigenvalues of E, and those bands will depend on kx and ky. So when I diagonalize E, I will have L different eigenvalues, which depend on kx and ky, and they are the bands of our system, and each of them has their own dispersion relation. Each band will have a different dispersion relation, which tells me how the energy of that band corresponds to the momentum kx and ky, and for different bands that relation will be different. So how do we diagonalize E? Well, that really depends on the structure of the problem. What do these matrices M, P, and Q look like? And that, in the end, is telling us about the geometry of our actual underlying quantum system. I can imagine even a simple square lattice of individual atoms, but each atom, in reality, has more than one electron. We're not talking about a lattice of hydrogen atoms. So in a real system, even a square lattice would involve many atomic orbitals on each atom, and each of those atomic orbitals has some energy and some coupling with neighbouring atoms and so on. So in real systems, you do have many electrons per unit cell, and you do therefore have many bands. And the relation between the energy of each band and momentum is exactly the information contained in the band structure. So the punchline is we're not quite finished yet. To understand the band structure of our solid material from the fundamental model, we need to do one final step. We need to do another canonical transformation of our C operators. This time let's call them F operators. They still depend on the momentum kx and ky, and the transformation that takes the C's from the F's, which is parameterized by this unitary matrix U, will also depend on the momentum kx and ky. We substitute that expression into the Hamiltonian, and this is what we obtain. And the whole point is that we choose, for each value of kx and ky separately, we choose a matrix U such that the combination U, E, U is a diagonal matrix D, which of course still depends on momentum x and y, such that this matrix D is a diagonal matrix. Let me give elements of P primed. They're going to be equal to the delta function P primed. We want it to be diagonal. And the elements along the diagonal are going to be the energies, finally, of the system. They're going to be given a label epsilon for energy. They're going to depend on kx and ky, and they're going to have a band index P. So they're going to depend on momentum and on which band we're talking about, labelled by P. And so finally, we've managed to fully diagonalize our system. We have a sum over momentum in 2D space. We have a sum over bands. And now we know exactly, in a very technical and precise way, what a band means. They are the energy eigenstates of the system as a function of momentum, and there are L in total. So L is the number of degrees of freedom in the unit cell. So there are the same number of bands in my solid as there are degrees of freedom in the repeating unit cell of the lattice. This term here is the dispersion of each band. So for each P, labelling the band, I can now work out, or I now know, what the energy-momentum relation is. And then finally here, I have the number operator for a given band P and momentum kx, ky. And written out explicitly, here we have the dispersion in terms of the original matrices M, P, and Q, and all we need to do is to find these diagonalization coefficients contained in these U matrices. And since the band dispersion relation here involves momentum-dependent factors e to the I kx and e to the I ky, these things are, of course, 2 pi periodic. So the band structure we have is actually defined in momentum space up to 2 pi, and then the whole thing repeats again. So let's take as a simple example a system where we have 5 degrees of freedom in each unit cell. that would mean that I could draw a band structure diagram where I plot the energy as a function of kx and ky, and then here on this axis I will plot kx, and of course I have another axis extending out here which is ky, but let's just imagine a slice through the whole plane at ky is equal to 0, for example. And then I'd just have a two-dimensional band structure diagram. So these would be cuts at fixed ky as a function of kx. And I look at the band structure. And indeed, in complicated systems, often people take a certain route through the Brillouin zone from different high symmetry points. So they might not just have ky equals 0, they might take a particular route through momentum space to exhibit the band structure. And so because I have L equals 5, I have 5 distinct bands which I can chart the energy of as a function of momentum. So for example, I might have some band that looks like this. This is little l equals 1. And then I have a different band that does something else, l equals 2. I have a third band, maybe the third band even slightly touches and moves off, l equals 3, and so on. And I can label these different bands by this index, L. Indeed, in real crystal lattices, often it makes sense to label these bands by the symmetries of the underlying lattice. And so here, these labels would actually have some physical meaning. We'd be able to say that this particular band was the one with spherical S symmetry, and it was made out of atomic orbitals that had this particular symmetry. And so we can actually attach meaningful labels to these various bands. And they're to do with the symmetry of the actual lattice in real space. Here I'm just labeling them by some arbitrary index that just runs from 1 to capital L, the number of degrees of freedom in the unit cell. So in this system that I've drawn here, this is basically a metallic system, because if I look at any particular energy, for example, let's say my Fermi level, or my Fermi energy, sits here, then as I go across in momentum space, I see that several bands cross this Fermi energy, maybe even the same band several times, and this gives me an overall density of states at the Fermi energy, and that means the system is a metal. By contrast, in an insulator, I could imagine a certain band structure that has a gap in the bands, whatever they may look like. Again, I'm just sketching something totally arbitrary here for illustrative purposes. And what I see in this example that I've just made up out of my head is a situation in which there are no bands that cross the Fermi energy at any momentum, and therefore when I sum over all the momentum, there is no density of states at the Fermi energy, and therefore this system would be an insulator. It would cost a finite amount of energy to promote an electron across the gap, and indeed we can identify what the minimum gap is. We can see, for example, at this particular momentum, there is a particular energy gap, delta E. Over here, the delta E is much bigger. Maybe if I just exaggerate this diagram at this end, maybe you would see that there was a minimum gap somewhere, delta E. And that would be the overall gap in the density of states once you take into account summing over all momentum. And again, as I mentioned, this whole thing is periodic in 2 pi, so these bands should actually join up. So the value at kx equals 0 should be equal to the value at kx equals 2 pi, and so on. So I've not drawn this very well. To make these things match up, I have to be a bit more careful. Okay, that looks roughly right. And of course, for a two-dimensional system, these bands are actually surfaces in the kx, ky plane. Here I've just drawn a cut at fixed ky is equal to 0, and so they look like lines, but for a two-dimensional system you'd have two-dimensional planes of bands, and for 3D you'd have hypersurfaces. So as a simple limit of this, we can actually go back to the 2D square lattice with a single orbital. So this is where we have 1 degree of freedom in each unit cell. We can therefore write the matrix that describes the coupling within the unit cell is of course just a 1×1 matrix or a scalar. We can write that as, for example, the energy of that side. Let's write it as the chemical potential mu. We can write the hopping matrix element, the tunneling matrix element along the x direction, which is described by the P matrix. Again, it's 1×1. Let's say that is a tunneling amplitude T, and let's say the tunneling amplitude along the y direction, let's give that a different value, let's call that T primes. This then gives us a dispersion for the single band in the system. Again, it's a 1×1 matrix or a scalar, which, just reading off from our previous formula is this. And T primed for the coupling along the y direction. Which can also be written as a constant energy shift for the chemical potential mu plus 2T cos kx plus 2T primes cos ky. So reading off from our previous formula, it's extremely simple. Let's just draw the dispersion relation. We'll consider mu being chemical potential in the middle, and we have a band of states between mu minus 2t and mu plus 2t, because these cosines can take a maximum value of either plus or minus 1 in their magnitude. And then we can plot in momentum space. We can see that they're 2π periodic. Let's plot kx. Let's plot kx at ky is π/2, just as an interesting thing to look at. It's 2π periodic, so I'm going to get a graph that looks something like this. And the dispersion is going to be something that has this cosine form and looks something like this. And of course we see that this is a metal because everywhere inside the band we have a finite density of states. So if mu is the Fermi energy in particular, then we see that the Fermi energy, there are bands that cross the Fermi energy at these 2 points here and here, and therefore we have a finite density of states at the Fermi energy, and this is a metal. As another example, we can consider a one-dimensional system with a two-site unit cell, so L equals 2. Because it's one-dimensional, we just have a single momentum direction. We could just call it kx, or even just k as a scalar. But we will have two bands in this system because we have two different orbitals in the unit cell. This is the SSH model, and so we will have two bands, and we'll actually see that this is a band insulator. We already saw that by the brute force diagonalization of the Hamiltonian matrix, but here we can actually just do this analytically by using the Fourier transform to diagonalize in unit cell space, and then we'll have a 2×2 matrix E, which we can further diagonalize to find the dispersion relations. The dispersion relations will tell us for each of the two bands how the energy relates to the momentum along this one direction. So in the end, the Hamiltonian will take a fully diagonal form here, where I have the sum over momentum k and the sum over the two bands p equals 1 and 2, and the epsilon p are the dispersion relations for the two bands. Try to work this out analytically yourself, and you'll see, in fact, that these dispersions, of course, depend on T1 and T2. When T1 is equal to T2, we have a metal. When T1 is not equal to T2, we have a band insulator. And of course, I want to emphasize here that this is an infinite periodic system. So it's So I don't have an end to the chain. There's no part where the chain ends. There's no termination of this chain. This is an infinite periodic system. As we saw previously, it actually matters what happens at the end of the chain as to whether I get these localized states or not. That's another story. For now, we'll just consider the bulk of this system. So we want to know what is going on right in the middle of this infinite system. So let's go back to Mathematica now and just plot these dispersion relations for the SSH model in the bulk. And we'll see how the energy-momentum relation, the dispersion relation, depends on T1 and T2. So here I'm again using the Mathematica package to explore what's happening in the bulk of the SSH model. So I'm assuming that this is a periodic system. And you see here at the top that I've actually written down explicitly the dispersion relations for the two bands in this two-site periodic system. So we have two sites in the unit cell that's repeating in one dimension. So I've set T1 equals to 1, and the other parameter T2 initially here is equal to 0, and therefore we have a dimerized limit with two bands at plus or minus 1. But as I increase T2 away from 0, I see that the bands get some dispersion. The energies being plotted here as a function of momentum develop some momentum dependence because the different unit cells are coupled to each other, and I start to see these kind of cosine structures emerging. The system was gapped, but as T1 approaches T2, the gap closes and we get a perfect metal. We see as T2 is increased further, the gap reopens, and around the Fermi energy at 0, we have zero density of states. Okay, so what we saw there in the Mathematica simulation of this system is that if we have T1 not equals to T2, then we have two bands, P equals 1 and P equals 2, that have a gap. There are no states that cross the Fermi energy depicted as the green dotted line here for any momentum, and so this is an insulating bulk of the material. Likewise, for T2 greater than T1, and for T1 greater than T2, we see the same phenomena. This is an insulating bulk. It's only when T1 is equal to T2 and we have a fully homogeneous chain that these two bands kind of cross, and we have a gap closing, and of course at that point, which is a unique point in the phase diagram, we have a metal. Okay, so in this lecture we studied solving tight binding models. In the first part, we looked at how we can write down the Hamiltonian operator in a matrix form and diagonalize the matrix of Hamiltonian coefficients to find the single particle states and energies, and from that we can construct the many particle states and energies. This requires diagonalizing an L by L matrix numerically, which we showed that we can do for some simple systems. Next, we moved on to considering periodic lattice systems, which are good approximations to many materials. And there we have a situation where we can perform the diagonalization exactly analytically using a Fourier transform, because we have a relation between real space and momentum space, and we know that momentum is a conserved quantity in these systems up to the lattice constants, because of course we have translational invariance, and we know that Noether's theorem connects the lattice in translational invariance to the reciprocal space of momentum on the lattice. We looked at more complicated unit cells, and of course this is in the end important, apart from the simplest toy models, because even simple geometric lattices of real materials are made out of atoms, and the atoms have more than one electron occupying different atomic orbitals, and so we always have multiple degrees of freedom per unit cell. And the number of degrees of freedom in the unit cell is exactly the number of bands in our band structure. And we understood that a band structure is nothing else but the diagram showing the fully diagonalized system with the energies of the different bands as a function of the momentum of the system. And we looked at a couple of simple examples of that.